Thanks for coming back for part 2. So, as promised, I want to talk about 2 of these really big applications and examples of 2 Segal objects. So, as I hinted at a bit in the first talk, so one really interesting thing that happened in the development, we had these 2 groups of authors that stumbled on this concept at the same time, even though they defined it differently, they had different motivations. But they kind of had one really prominent common example that emerged pretty quickly in both of their work, and that is the output of the S-dot construction when applied to an exact category. So that's what I want to do in the first part of this talk. So let me remind you just, I'm not going to give you the definition of an exact category, because in the end, we're not even going to use the full structure of it. But you can think of it as, well, it's a category with a notion of short exact sequences, a bit weaker than an abelian category. And if we have such a category, we can define, well, we can take its Grothendieck group, K0, and this is just the group generated by the isomorphism classes of objects. And then we have this relation, so whenever we have a short exact sequence, say A to C to B, then we want to make the identification that A plus B is equal to C. So we're sort of modding out by that information. And then, well, people then wanted to define higher algebraic K-theory groups. And what proved, starting with Quillen and other people, the way they did this was sort of to build some kind of space whose homotopy groups were the higher homotopy groups. And one approach to that uses, well, the following features of an exact category. So this is what's really going to be important for us. So the first is we have 2 distinguished classes of morphisms. So we have admissible monomorphisms, which I'll write with a little hook, and admissible epimorphisms, which I'll draw with the sort of the 2-head arrow. And these are the things that appear in the appropriate places in your short exact sequences. If it was an abelian category, they'd really be monomorphisms or epimorphisms. But here we just say, okay, they sit in the appropriate place in a short exact sequence. So that's the first thing. We're going to have all these decorated, 2 kinds of decorated arrows running around. We have a 0 object, so it's both initial and terminal. We'll denote that with a star. And then we're going to say we have commutative squares. So here are our horizontal arrows are our admissible monos. Our vertical morphisms are the admissible epis. And these are push-outs if and only if they are pullbacks. So in other words, they're bipartition. And, well, because you're using push-outs and pullbacks, anytime you have flattened them to fit them on the slide, but anytime you have sort of the span, sort of the left hand and the top arrows, then that can be completed, well, essentially uniquely. Generally say up to isomorphism, I can complete that to a square by taking the push out. Similarly, if I take the cospan given by the bottom arrow and the right arrow, I can take the pullback, and that will determine a square as well. So these are the features we're going to be interested in. So, sort of canonical example, which is in fact abelian, is just the category of R modules. For a commutative ring, you take the usual monomorphisms and epimorphisms. So you can keep that one in mind. But in fact, I mean, I've sort of distilled down the things that I'm going to want to use. And Dyckerhoff and Kapranov say, let's just take that structure, basically all the things I listed on the previous slide, and call it a proto-exact. So it's just, but you don't, so unlike an exact category, there's no algebraic stuff, the stuff I haven't defined because it's not really relevant for what I'm going to do with it. And so you can get non-algebraic examples like the category of pointed finite sets. So this would form a proto-exact category. The admissible monomorphisms are just the injective maps. And the admissible epimorphisms is a little more quirky. So these are the surjective maps, but the pre-images over things that are not the base point are just singletons. It's kind of just what it has to be. This ends up forming a proto-exact category. It's not exact, but it behaves in the ways that we. Okay, so with this data, I can tell you what the S dot construction is. This was originally defined by Waldhausen. Well, this is a slightly adapted version of how we define it. I'll say a little bit more about that in a bit. So let me take just a proto-exact category. So anything that has these features that I've described, and we're going to take S sub n of C to be the groupoid of diagrams in C of the following form. So the things to notice, we've got this sort of triangular wedge here, all along the diagonal, we have the zero object. And in particular, those maps sort of to and from are the unique ones using the fact that it's a zero object. We've got the admissible monomorphisms going vertically. We have the admissible epimorphisms going vertically. And we ask that all the squares, we ask the diagram to commute, but we also ask for all the squares to be biclick. And then, well, the groupoid structure says, well, if I have another such diagram that is pointwise isomorphic, such that everything in sight commutes, then I'll take that to be an isomorphism between the two diagrams. So we get a groupoid of such things. Okay. So in particular, if we take S0, so if you look back, the first thing that has an index that's A0, 1, you should think of the diagonals as being A0, 0, A1, 1, and so forth. If n is 0, then all I'm getting is just the groupoid of 0 objects. Groupoid just because they're unique up to unique isomorphism. Could be multiple of them. Then, well, S1C by definition is the groupoid of diagrams of this form. But, well, the star is just the 0 object, and so sort of the data of the maps is, essentially determined. This is just really the groupoid of objects, sort of the maximal subgroupoid on all the objects of C. Then if we move up to 2, so we get all diagrams of this form. But again, if you're saying, well, everything involving a star is just the unique maps, what am I left with? Well, I have an admissible monomorphism from A01 to A02, an admissible epimorphism from A02 to A12. And well, this is really just the data of a short exact sequence. If you're in something like an exact category, where you talk about that. So this is just the groupoid of short exact sequences. Okay, and these assemble together into a simplicial groupoid, and I'm often just going to sort of slide over into simplicial spaces just by taking the nerve of that groupoid, so I get a simplicial space in that case. So, but if I claim that, then I need to say something about the simplicial structure. So again, here's a 2 simplex, is something like this, and if I apply the face maps. So similarly to the things we talked about earlier, the D0 and D2 are given by sort of some kind of truncation, and D1 is some kind of, combining. So D0, I just chop off that top row. So everything that has a 0 index, which is just the top row, and I'm just left with sort of this bottom row here. Similarly, D2, I'm just chopping off the right-hand column, and I'm just left with this. So the D1 is a little weirder, but we think of, all right, I'm going to remove everything that has index 1. So that would be A01, A12, and then also this star here, which would be in slot A11. And then I just replace, say, I take the composite map from star to A02. So I'm left, and then similarly the composite. So that's what the interface is. Okay, and then degeneracy maps are given by inserting identities. So here's a one simplex. And I can either sort of take that one simplex and insert it at the bottom and just sort of complete it to a two simplex in the silliest way I can think of. So just duplicate the A, duplicate the star. I don't know why I put that epimorphism there. That could just be another equal sign there. And then, or I can insert it up in the top level and again, just complete it via identities and duplications. So. Okay, so that's the simplicial structure. Okay. All right, so then, again, I can think of this S dot as a simplicial groupoid. I can geometrically realize to get a simplicial space. And then, well, I'm thinking of it as a simplicial object in simplicial sets. I can just take a diagonal, think of it as simplicial space. There's a construction for a realization. So I've got bars around it. This is just a simplicial set or a topological space. To make it easiest here to think of it as a topological space. And if what you're starting with is like an exact category, then you can check that if you take its fundamental group, that is just this Grothendieck group that I described earlier. So, but if we want higher K-theory groups, we can say, all right, let's take this space. Well, I kind of don't like the fact that I have a K0 on the right and a pi1 on the left. So I just take loop spaces so to bring all the homotopy groups down and say, all right, I want the K-theory space to be the loop space of this realization of S dot. And then we define the K groups of C to be the homotopy groups of this space. So they're either the homotopy groups of K of C as we've just defined it, or if you want to go back to S dot, you just end up with this shift. Pi. All right, so that's really all I'm going to say about the K theory, but sort of, why we care about S dot constructions, why they're important. And this is, there are lots of ways to define K theory spaces. S dot is kind of one of the more general ways to do it, and it specializes to some of the other ways that they're. Okay, but what we're interested in here is not, okay, what are the K theory groups of things? Interesting as that is, we're interested in, well, let's go back to the simplicial space before we take this realization and just look at the structure. And this is this main theorem of Dyckerhoff and Kapranov and Galvez-Carrillo, Kock and Tonks, is that if C is a proto-exact category, then this S dot C is a two Segal space. Or you can think of it as a two Segal groupoid, if you like groupoids in the original. Okay, so why is this two Segal? So again, let's just look at this map, D0, D2. So this is going to go from S3 to two copies of S2 agreeing along S1. So using the way we've defined the face maps, now we're on a three simplex. D0 is going to do the same thing it did before. We're just going to chop off the top row. So this diagram down here in blue, that is D0 of the whole three simplex. Now D2, if we're taking for a three simplex, D2 is an inner face map, and we remove this L-shaped region. So we remove everything with a 2. So that's A02, A12, this 0 object, and A23. And so when we take these composites, we get the diagram in red. So on the right-hand side, we get the union of the red diagram and the blue diagram. So what is missing? It's A02 and then those three black arrows. So if this is to be two Segal, then I should, given the data of the red and the blue, I should be able to reconstruct essentially uniquely, I should be able to reconstruct the whole 3 simplex. And I can do that by saying, look, I've got, if I look at the red and the blue, I've got this blue arrow from A12 to A13. I have the red arrow from A03 to A13. That is a cospan. I can take its pullback. So that gives me A02 and the 2 arrows that come out of it. And then by the universal property, I can get that remaining arrow from A01 to A12. And since we're in, I mean, we're not in the strict case anymore, and the pullback is defined up to isomorphism, but we're in this groupoid or space world, so it's fine that it's not defined strictly. This map just needs to be a so that's why it's 2 Segal. But it's not so interesting to be 2 Segal if it were 1 Segal. But it's not. So what would it mean to be 1 Segal? Well, we need the 1 Segal map to be an equivalence. Well, the image of the 1 Segal map looks like a staircase diagram like this. I have 2 1 simplices glued together along the 0 simplex, which is just a 0 line. But this little configuration that we have here is not, this is not a span or a cospan. It's not something that we're guaranteed we can complete. And in fact, if we're thinking about 2 simplices as short exact sequences, completing this diagram is basically finding an extension of A01 and A12. Well, in general, that's not unique. So being 1 Segal would mean that all your short exact sequences split. So we're definitely in general not 1 Segal. And I mean, there's also a question of, does it exist? And if you're coming from something really algebraic, R modules, well, then you can always complete it just by the direct sum. If you're in a, one of these weirder proto-exact categories as possible, maybe you can't even complete it at all. All right, so one question, you can say, well, how far can we push this? We pushed from, exact to proto-exact. Can we push this further? So what is the maximal input? The most general thing we can feed into the S dot construction and get something out that is 2 Segal. So for example, I said this S dot is originally due to Waldhausen, but not quite in the way that I've described it. So Waldhausen's original input was a category with co-fibrations. So, and then, so there's only one distinguished class of morphisms, analogous to our admissible monos, and you have push-out data in his axioms, but you don't necessarily have you don't have a second distinguished class, you don't know anything about pullbacks in general. So my student Tanner Carawan just posted a paper last week or so on the archive with this result. So if you have a category with co-fibrations, then S dot C is what's called lower 2 Segal. In the sense that the 2 Segal maps corresponding to triangulation with all diagonals meeting the vertex 0 or weak equivalences. Okay, that's a bit of a mouthful. Let me go back to here. So this was the 2 Segal map D0 D2. Now if you go back to my last talk, this was the triangulation where you have an edge from 1 to 3. Well, this would not work. If all I can do is take pushouts, I could not complete this diagram anymore. Because in order to complete this diagram, I needed to take a pullback. So if all I have is co-fibrations, I can't guarantee that I could do that. But if I took the other map, the D1, D3, that's a dual diagram that I would complete by taking a pushout, and that would be okay. That's coming from the diagonal that goes from 0 to 2. So what he's saying is, well, some of the map, if all you have is a category with co-fibrations, then all you can guarantee is that certain, basically it's going to be all the diagrams that you could sort of reconstruct with pullbacks you can do, but no guarantees that you can do that. So this is too much, you know. We've gone beyond the maximal input. We've gone to something where we don't get something too Segal anymore. Okay. So again, to just try to not do too much generalization all at once, I want to go back to the S-dot construction, but I want to look at a very strict discrete version. So, you know, take something like an exact category, and instead of taking the groupoid of these diagrams, just take the set. So I'm not remembering if they're isomorphic or anything like that. I'm just going to take the set. Base and degeneracy maps are just like before. S dot's going to be just a simplicial set. But this is very unnatural. Warning, you know, this is very unnatural because these squares really need to be absolutely, completely, uniquely determined. So pushouts and pullbacks are unique. But I'm trying to keep the abstraction under control, at least temporarily. Okay, so we claim that we can, for this discrete version, we can generalize the input beyond what we had before. So to something we call a pointed stable doublet category. Okay, so what is this? We're going to have objects, and we're going to have two kinds of morphisms, and these are going to form what's called a double category. So a double category, I mean, you've heard of categories internal to categories, that's what it is. But what it means is you have sort of two flavors of morphisms, but unlike an exact category, a proto-exact category, they don't need to live in a common ambient category. They're not just distinguished classes of morphisms in some common category, but it's a structure where we have objects and we have one kind of arrows and they form a category of some other kind of arrows, they form a category, and then they fit together into squares with horizontal morphisms going horizontally, vertical maps going vertically. And this is part of the data. You just, you know, we can't talk about commutativity, we can't talk about Cartesian, co-Cartesian, we can't talk about that anymore because they don't live, we can't compose, they don't live in the same place. But it turns out we didn't really need that. So that's what the double category is. So we have this square. Pointed means we want to have something like the star object. But if you think about the diagrams, you know, we always end up mapping out of them with the horizontals and into them doing with the verticals. So we don't need it to be a zero object in both categories. We just say it has to be initial for the horizontal category and terminal for the vertical. And then stable, well, this is our fix to the fact that we can't talk about pushouts and pullbacks. So we say we have squares and so the squares are just part of the data of a double category. If it's stable, we say anytime we have the span, sort of the upper left span, we can uniquely, in this case, completely, strictly, uniquely, complete that to a square. So that's like having a pushout. Or if we have the cospan in the lower right, we can complete that, so sort of like taking a pullback. So completely unique, and that's the stability. And so we claim that this is, it's a more general data, it's more general data, but this is enough that we can make sense of the S-dot construction. Okay. So observe, so notice, you know, when we take Sn in degree 0, we just get the, well, in this case, completely unique zero object. So, well, the two Segal set that we're going to get from this is always going to be reduced in the sense that S0C is just going to be the point. So we're not going to get anything that doesn't satisfy this, but this result they proved with Angelica Sorno, Victoria is one of them, Martina Rovelli, and Claudia Scheinbauer, is that this discrete S dot construction defines an equivalence of categories between pointed stable double categories, these things that I just described, and reduced two Segal sets. So in some sense, this is the maximum input. This is the most general thing that you can feed in, and you can get something out that's two Segal in this discrete setting. Now, you might be unhappy with the reduced part. There is a more general version, and this is what we actually prove so that you can get something. You want to get all two Segal sets, and you end up having something called augmented stable double categories. I'm not going to get into that. It's a little bit of a weird condition, sort of like having a local initial or locally terminal condition on some set of objects. All right, so let me say a little bit about, I mean, this is an equivalence of categories, so you could say, well, what happens to the inverse function? So if I have a reduced two Segal set, say, hey, what does its corresponding pointed stable double category look like? Well, K0 is, I mean, it's reduced, so it's just a single point. That's going to become my distinguished object. K1, the one simplices, they are going to be our set of objects. So this is the common set of objects for both the horizontal and the vertical categories. And now, in an abstract way, the horizontal and the vertical morphisms are both, if I just, aside from any structure, I just look at them as like just sets, they are both given by the set K2 of two simplices. As we'll see, they're going to behave rather differently from each other in their structure. And then K3, the three simplices are going to determine the squares. So more formally, this is what's called a double path space or a double Dyckerhoff. So if you've seen that, that's what's going on here. So let's look at this. Earlier this morning, I talked about this example of two Segal sets associated to graphs. And we had our running example, G, this 3 vertex 2 edge graph. And so we can say, all right, so we obtained a reduced two Segal set from that. What's the associated pointed stable double category? Well, its objects are supposed to be the one simplices. Those were just the subgraphs of G. And both the horizontal and vertical arrows should correspond to two simplices. So these were subgraphs with a partition of the vertices into two sets. But this is where we can see. So let's take a two simplex. Here's an example we've seen before. So we have the subgraph with one edge between A and B. We have A in the first set in the partition, B in the second partition. Again, blue comes before orange. And this is supposed to represent, well, it's going to represent a horizontal morphism and it's going to represent a vertical morphism. So the way that it represents a horizontal morphism is it's going to go from A, which is just whatever's in the first set in the partition, to the whole subgraph. I mean, so remember the objects are supposed to be given by one simplices. So we're taking one simplex that is, well, I guess that's D2, and then this is D1 where you merge them. So it's a horizontal morphism between those two things. But the way that it represents a vertical morphism is between the whole thing down to the singleton B. So it's going from like D1 to D0. So it's involving the other thing in the partition and the arrow is going a different way. So the structure of the horizontal and the vertical categories is quite different from each other, even though abstractly the collections of morphisms are excellent. Okay, and the squares get a little crazier. I couldn't even fit this all in one slide. So again, here's a three simplex, giving you a well, it's actually the whole graph. Three simplex on that, so that they're all interesting. This would correspond to the following square. I don't know what what to say exactly. So, but you're saying, all right, I have these the arrows are all corresponding to two simplices. These are the different. These are the four faces of that three simplex, and then, well, in the way that we just described, each of those two simplices, you know, has an interpretation as a horizontal or vertical morphism, and you can see those, you know, kind of appearing. I mean, I guess over here on the left, we literally see one of the maps that we looked at. So there's a very formal way to describe this functor. Not going into that, but giving you just a sense of how these things look. That you can, in these small, discrete examples, you can really explicitly write down what's going on, and you can see what you get, which is kind of fun. Okay. Now, I don't like this discrete version of S dot because it just has, you know, these pointed stable double categories are so strict. You know, things having to be actually unique, it's just not applicable in real life, real mathematical life. So we need a homotopy version. We need a two Segal space version. So we make everything that I described before homotopical. So we say a pointed stable double Segal space. So this is now a bisimplicial object. So it's a functor from delta up across delta up into simplicial sets, spaces if you prefer. And this is, so X is a Segal space or a one Segal space in the sense of the last talk in each variable. So remember, a Segal space was something that behaved like a category, but up to homotopy. So if I want a double category, then I need to have sort of a vertical and a horizontal category. So I just say, well, I have this bisimplicial thing. If I restrict either, you know, if I fix an object in one of the copies of delta op and I let the other one vary, I should get a Segal space. That's going to give you, well, either horizontal or vertical, depending on how you've done the restriction. So that's how I make the double category sort of homotopical. And now we're back, but with things like the pointed, this is maybe a more familiar version. So we have a contractible space of objects that are initial in the horizontal category, terminal in the vertical category. And squares now, these are going to be objects of x1, 1. So I guess, I mean, the objects will be x0, 0, then horizontal and vertical will be x1, 0 and x0, 1. So the squares are objects of x1, 1, and they satisfy, again, what's probably actually more comfortable, an up-to-homotopy version of stability, in the sense that these behave like pushouts, they behave like pullbacks, but they're not strictly unique. They're unique, you know, up to. Okay, so with the same co-authors, following paper that we showed that the S dot construction defines, so this is not an equivalence of categories anymore, but an equivalence of homotopy theories. So this was actually realized as an equivalence of model categories, but I chose not to talk about that in this talk series. But so just suitable notion of equivalence between pointed stable double categories and reduced two Segal spaces. And here, again, reduced would mean in a suitably homotopical sense. So x0 may not be literally a point, but it would be a contractible. And, well, if you're going to go through all your trouble of abstracting things, you want to know that it's not something completely new. And so this in fact does recover S-dot constructions that we, knew and loved before. So the version that I described at the beginning of the talk for exact categories or proto-exact categories, or if you want to take versions in the literature for, proto-exact quasi-categories or something like this, this is a common generalization of all of them in a suitable way. So you can take the inputs to all of those, have some kind of double nerve functor that lands in the, and all these examples, in fact, they end up being pointed, and you can show that it recurs this. And again, if you want to drop the reduced assumption, you can replace pointed with augmented. And again, the inverse functor is again given by some kind of suitable double path space construction, now defined. Okay. So that's all I want to say about the X-dot construction. So on to the second main application. So classically, Hall algebras. So these associated to some nice abelian categories. So sufficiently finitary, where the multiplication essentially is counting short exact sequences. So again, we're seeing short exact sequences popping up. It's maybe not entirely unrelated to things that were used before. For counting, this finitary is basically counting, so that we actually get a number when we count the things, and things are well defined. So these classical algebras, there's generalizations, derived Hall algebras, motivic Hall algebras, things like that. And this was a big motivation for Dyckerhoff and Kapranov, was to say, okay, what's the unifying framework? What makes these other things Hall algebras, other than just, they kind of look similar? And they say, well, maybe with some appropriate restrictions, we can say take a 2 Segal object and get an algebra from it that could be called a Hall algebra. So I want to start just by talking about the classical ones, just for some motivation. So, so in this case, finitary here, this is really an abelian category. Take it to be finitary, which basically just means that all our Hom groups are finite, all our X1 groups are finite. A lot of the examples just aren't higher X groups. And we define an algebra. So as a vector space, this is going to be over any field, is spanned by the isomorphism classes of objects. And then we define the multiplication as follows. And so we say, well, if I have an isomorphism class A and B, I define their product to be a sum over isomorphism classes C, and then I have some coefficient. And what the coefficient is doing is counting all the short exact sequences. So it's counting the extensions of A by B, and then, we're going to mod out by the order of the automorphism group of A and B. We basically just want the extension data, not things about it. Okay, and this turns out to define an associative unital algebra. Okay, so a common source of these, and why people got pretty excited about them, was that you can associate them to Lie algebras. So if you take a Lie algebra of type A, D, or E, it has an associated Dynkin diagram. It's ADE, it's simply laced. So for example, we have the A3 Dynkin diagram, and you can, however you like, give an orientation to the edges. This gives a directed graph or a quiver. So for example, I can put the orientation on there that I just did. And then if I take representations of that quiver, which you might think of as, if I think of that as maybe category, and I just take functors into FQ vector spaces, then this gives an abelian category. So here's a typical representation of this quiver. So I might have, FQ squared, FQ, and FQ cubed into FQ. Anyway, those form an abelian category since we've taken a finite field. And well, the fact that we've chosen a simply laced Venn diagram, things are well behaved. And we have a nice ball algebra, and why people cared about this is it ends up having a very close relationship to the quantum group. And this is results of Ringel and Green. That's your crash course just for motivation. I'm not going to go into more about that. But what I want to do is reinterpret this in light of things that we talked about earlier in this talk. So a finitary abelian category in particular is an exact category, and therefore I can take the S dot construction of it. So just first part of the slide is just recapping something I said earlier. So this is S dot is a two Segal groupoid, geometrically realized to get a two Segal space. S0 will just be the groupoid of zero objects. S1 is the groupoid of objects. S2 is the groupoid of short exact sequences. So recalling things from the talk, we can define composition via this span. So we have S2, we have the map. I guess I flipped to D2, D0 there, and then I've got D1. So if I'm thinking of an element of S2 as a short exact sequence, then this left-hand map is going to send it to the pair AB. The right-hand map is going to send it to C. So that's the composition in the two Segal space that's partially multiply defined in the way that we talked about in this talk. Okay, but I can get an algebra from this. So I'm going to take finitely supported functions from, so S1 of A, if I think of it as a space, I just take pi 0, leave it as a groupoid, take its just set of components, and just take finitely supported functions from that to a field. Here I don't care what the field is. And that's going to define a vector space that I'll just denote with the exponential notation. And so I claim that we get a multiplication as follows. So I'm using this span here. So if I have a function, so F, so this should be, well, it's a pair. I can either think of it as a pair of functions from pi 0 S1A into K, or just a function from the product of two, ends up being isomorphic. The product of two copies of pi 0 S1A and map it into K. Let's denote it by F. And where that's going to go, I'm going to just pull back along the D0, D2, and then I'm going to do a push forward along D1. And some of this, finiteness assumptions on A are going to guarantee that everything here is going to be defined. And so what's going to happen when I'm not doing the two individual steps here. I'm just saying what function. I want to start with something on the left-hand side. I want to get a function that inputs, well, an element of pi 0 S1A. That's an isomorphism class of objects. So say C. And I want to send that to an element of the field K. And that where I'm going to send that is a sum over isomorphism classes of short exact sequences whose middle term is C. And then I'm going to send that to, well, what is F of D2, F composed with D2, D0? That's this pullback here, and then feed in S. That should be an element of the field. And notice, but if I take that composite, what is D2, D0 of S? That's just F of A comma B. And I guess technically I probably should have put little brackets around these because I want to think of them as elements of pi 0. So they're isomorphism classes of objects. And if I take the special case, let F just be the characteristic function, of those isomorphism classes 1A and 1B. Reinterpreting what I just wrote, I get, well, a sum over isomorphism classes of objects C, sum over short exact sequences with C in the middle. And then that's going to be a sum over characteristic function of C. And that's going to, but okay, counting those short exact sequences, that's exactly this GCA. So that's going to recover the classical definition. Okay, and so the same kind of definition is going to work. Again, you need to have some finiteness assumptions, so all the summations that I've defined are going to actually give you, be well defined. And those are gonna get, but you're gonna get something, but you have to feed in something that's reduced in order to get an algebra. If you have a 2 Segal object that is not reduced, then you would get, well, like an algebra with many objects, so an algebraic or K-linear category. Yes.
GABC was the number of these elements modulo of the automorphisms of A. And
Yeah.
where are the automorphisms?
Yeah, I mean, it's sort of packaged in the fact you're taking isomorphism classes of, I mean, you're taking functions and that's not going to depend, you're kind of losing that automorphism data in the way that I've defined the functions anyway. Yeah, I mean, there's probably a little bit of the
Not all automorphisms on both sides will extend to something of the extension. So,
yeah, I mean, I might be fudging a little bit here. Yeah, there might be little things here. I'm trying to give the idea. So yeah, it's possible there's something that slightly needs to be tweaked. All right, so let me give it the abstract definition. So if I have a reduced 2 Segal set, and let me just give a very safe finiteness assumption, which is there's finitely many simplices in each dimension. Then we're going to define its Hall algebra, H of X, again, over a field, whichever field I like, doesn't really matter. This will be the K vector space, generated or spanned by X1, whatever the one simplices. I'm trying to abstract what we did before. And then its multiplication is given by a very similar formula. So if I have an X and a Y, these are one simplices. I want to take a sum over all possible one simplices Z, and then I'm going to have this coefficient, GZXY. And what this is going to count, now remember, before we took S dot of something, so our short exact sequences became 2 simplices. So what I want to do is count the 2 simplices, so the number of 2 simplices sigma, whose D0 is Y, whose D1 is Z, and D2 is X. Again, when these were coming from short exact sequences, that's exactly where I had, X and Y and Z in the middle. A and B and C as I did with them before. So this is the abstraction of what I did before. And Dyckerhoff and Kapranov proved that this is in fact an associative and unital algebra. And the associativity is really coming from the 2 Segal condition. The associativity that you have there is going to be associative. All right. So what's nice about this, if you think about this, like FQ representations of a quiver example, I mean, these end up being huge algebras. And so what's fun kind of about this definition is you can take some very baby examples and you can really explicitly say, well, what the algebra is. So let's go back to our 2 Segal sets from graphs. Let's take an even smaller graph than we did before. Just take A and B with one edge. So this is, as a vector space, it's 5-dimensional because we have 5 subgraphs. So we have the empty one, We have the singletons A and B. We have just the disjoint union of A and B, and then we have the whole graph. But it's only non-trivial multiplication. So again, let me notice, I can only multiply things. I can only get a non-trivial multiplication x, y if there's a two simplex where D2 is x and D0 is y. In these graph examples, that means those subgraphs have to be disjoint from each other. So I can only interestingly multiply subgraphs that are disjoint. So the only things I can multiply are the singletons, A and B. And if I do that, so this goes back to when I talked about non-one-sigality, remember, well, that could come from a two simplex, that's just the disjoint union of A and B, or it could come from G where I have the edge. So I have the sum of those two possible things. Well, they're the D1 of them, I guess, of those two simplicities. But that's actually the same as multiplying B with A. Now, when you go to cook up the two simplex that that comes from, your partition will be ordered oppositely. But, well, the Hall multiplication isn't remembering the partition, it's only remembering sort of when you pass to the subgraph that you get. Okay. In contrast, I mean, let's just take the graph with a single vertex A, and then it has a single loop. Now you get a three-dimensional vector space. We've got three subgraphs, the empty ones, the vertex A by itself, and then A with the loop. But there is no, oh, and by the way, I should have said this earlier. I mean, the empty subgraph, I mean, that ends up being the unit element in the algebra. So that's why there was no interesting multiplication with it, because it just behaves as a unit. In this case, there is no non-trivial multiplication because there are no, I can't choose two subgraphs that are disjoint from each other, other than the empty one. And that multiplication is not interesting. So because A and G, they share a common vertex, I can't put them in a two simplex, interestingly. Okay, so here's just, you play around with this, you know, you can get the following properties of their Hall algebras. So if you have subgraphs H and K, if they're not disjoint, then their product in the Hall algebra is 0. Again, that's just, they can't be a D0 and a D2 if they're not disjoint from each other. So the multiplication has to be 0. If they are disjoint, then their product is a sum over subgraphs J, where J is, well, it contains the disjoint union of H and K, but it might have additional edges connecting vertices of H to vertices of K. So the idea is you have some subgraph J, and then you get H and K via partitions. So you have the vertices of H in one and K in the other. When you take those space maps, these other edges disappear, but you could possibly insert some of them in the original graph. That's what the J is. In particular here, these Hall coefficients are always either 0 or 1. There either is a two simplex with these two subgraphs as appropriate bases, or there's not. There's no way to have them with multiplicity in this example. And as we saw in our first example, this is commutative. Okay, so that's, you know, that just gives you a flavor. There's lots of interesting things that you can do here. You know, in particular, if you go back to this classical example that I gave, they were really working in two Segal objects and groupoids, and then you reduce down to, you know, you take pi zeros in order to get an actual algebra. So you can get much fancier things if you retain more sort of homotopical data, and that's a large part of Dyckerhoff and Kapranov's higher Segal space management. So I will just finish talking about a couple other things related. So first, a couple things that I'm working on. So if you take cyclic two Segal sets, so, this is functors from Kahn's cyclic category lambda, we call them two Segal, if their restriction to simplicial things is two Segal. And something that Walker Stern and I have been working on is that these correspond to what you might call symmetric double categories. And this is where, you know, the horizontal and the vertical categories are actually, they're isomorphic as categories. They're not, or equivalent in a homotopy theory sense. So not just the sets, but they really end up being very symmetric to one another, which is kind of wild. So another thing, another project that I've worked on with Olivia Borghi, Eva Day, and Ima Galvez-Carrillo, Teresa Hoekstra Mendoza, we constructed a family of two Segal sets from trees. And by the way, I mean, I should say both that example and the one from graphs are sort of baby versions of constructions of Galvez-Carrillo, Kock and Tonks that come from combinatorics. Didn't kind of get a chance to say where that came from. But this is what's fun about this example. I mean, also that you get these very hands-on examples and you compute their Hall algebras and their corresponding, you know, pointed stable double categories. But if you have a tree, you can forget it's a tree and remember it's a graph. And you can say, well, I get a two Segal set from it as a tree, and then you get a two Segal set from it as a graph, and you can, you know, one sits inside the other. So it gives an example sort of sub two Segal sets, which is kind of fun. And then, you know, I always get asked, well, all right, you went from 1 to 2 and can you go higher? And it gets rather more complicated, but, well, basically you should come to Justin's talk later. I think he's not gonna talk too much about the abstract theory of them, but he's gonna talk about some nice examples from group theory. So if you're wondering, flavor of higher, what happens if you go higher than 2? And if you want more examples of kind of talked about, then you can come to this talk. First talk, right? So you should come to this talk. And so I will stop there.
Are there any questions or comments?
Then you turn two Segals, like you don't have the compositions well defined, but you have some span levels into emptiness. Right. Like, are there, for instance, can you use some duality, can you specify something to actually turn them into associative to some even algebras and spectra or something like that?
Yeah, so, I mean, yes, so you can do basically the procedure that I described for the Hall algebra. I mean, you can not lose as much information as I did by, you know, taking pi zeros and you get some kind of, yeah, I mean, another way to describe two Segal objects, you know, rather than saying, oh, it's like a category with partial multiplication, you say, oh, it's some kind of, you know, object, you know, algebra object in spans. That's another way to think about it. And it's a way to segue into thinking about, say, these like Hall algebras and Hall categories and generalizations. So. Yeah.
So you mentioned that the X-Stop instructions are polynomials. Could you briefly talk about what instructions are?
Oh, yeah, so the two Segal model structure, is basically, I mean, if you have, say, you start with, say, the greedy model structure on simplicial spaces, and you do a localization so that the Segal maps, the two Segal maps are weak equivalences. And then your five-unit objects are your like greedy five-unit two Segal spaces. The other, so for if you do the full version, the augmented stable double Segal spaces, it's again, you take delta cross delta. In order to encode either the pointedness or the augmentedness, you need to throw in another extra object. Like it's an extra terminal object to delta cross delta, we call that sigma. you take functors from that into spaces, and then you just do a bunch of localizations so that all the conditions, so that it's double Segal, and so it's stable, and so that's, I'm happy to talk more about it if you want, but yeah, it's all localizations.
Other questions?
Yeah, Paula, yeah, Paula, go ahead.
Just so two collaborators we have enriched as construction and the concept of algebraic theory of second.
Sorry, you have a what construction?
Enriched.
Enriched construction, okay, yeah.
So is there an account of this that is enriched, and also is there any other context in which this appear where it would be natural to want to have an enriched version of these two situations?
So, I mean, when I stated, I don't know if this exactly answers your question, but when I stated the homotopical version, I said, I mean, to keep it under control, I said spaces, but you can take, say, any, I mean, our proof is basically for some, suitably nice, say, model categories, take two Segal objects in C. Again, C is just something suitably nice and homotopical with finite, it's finite limits, something like this. So, and then you take pointed, stable, double Segal objects in whatever that C is. So that's actually the generalization that we prove it in. So you could interpret that as some kind of enrichment, but I don't know if that's what you're looking for. If you're asking for something beyond that, then no, I haven't thought about that, but it would be nice to, I mean, happy to talk about it.
Thank you. Good questions? Someone?
There was somebody.
I had a really silly question.
Sure.
If you go back one slide,
Mhm.
when you were advertising the talk this afternoon, it says D strictly bigger than 3. Should that be?
Oh, no, sorry, yeah, it should be,
There's
yeah,
nothing
it should
weird
be-
about D.
it should either be a greater than or equal to 2, I'm sorry, greater than equal to 3, or, yeah, so I should change one of the sentences. Either it should be greater than or equal to, although Justin think we're quite a bit higher than 3. So, well, yeah, so that's okay. 3 is perfectly good here.
Any more questions or comments? And if not, let's just thank you.